sixth lecture on beamforming technologies with phased array antennas, and it is the second day afternoon of ongoing 5G 5-day GAN course on wireless power transfer. Everything all about wireless power transfer antenna, device circuits, and application. I welcome again to Professor Naoki Shinohara for starting his lecture.
Thank you. よいしょ。So, welcome back to the afternoon's lecture. So, in this morning, I explained how to increase the beam efficiency. But at that case, we put a receiver just in front of the transmitting antenna. So, when we know where the target is, and when we put the receiver just in front of the transmitter, we have some way, some method to increase the beam efficiency. But this is a radiative wireless power transfer technology, and target or user will move somewhere. So what happened in this case, as I mentioned before, this radiative WPT is named the uncoupled WPT. So when user moves, we our transmitter cannot understand what happened in this case because there is no electromagnetically coupling. So beam is transmitting just in front. Beam keeps front beam in this case. So efficiency suddenly decreases. So how to keep the beam efficiency? We must control the beam direction. So we need a phased array antenna technology. Of course, if we have the mechanical antenna controlling system like the parabolic antenna or the other aperture antenna, we can do it. But if we move the antenna plane itself, accuracy is not good, and we need a very high power to move the antenna plane itself, and so there are some problems. So instead of the mechanical moving antenna, we propose phased array antenna technology. So this is one example movie of the phased array antenna in Japan. We've developed the phased array antenna in 2010, about 15 years ago. This is a transmitting antenna. And here you can see there is no movement in the antenna. And now at the receiver on the Japanese map, and here, please believe me, here is a microwave beam. And there is no movement on this movie, and we can control the beam direction. So this is our example of the hyper beaming and phased array beam controlling antenna movie. So this is our research equipment in my laboratory. So if you want to use this phased array, you can use it. And from here, briefly, I would like to introduce a theory of the phased array antenna. So phased array antenna is composed of this same antenna elements and controlling circuit. And behind the antenna, we put the amplitude controller and the phase controller named the phase shifter, etc. And from each antenna, we can transmit the radio waves, of course. And before the antenna, we control the amplitude and phase of each radio wave. And as a result, at the antenna, there are some phase and amplitude difference. And after propagating the radio wave from the antenna, as I mentioned again and again, we cannot do it anything. So because Maxwell's equation is perfect. So after transmitting a radio wave after antenna, based on the Maxwell's equation, all radiated waves are merged based on the amplitude difference and the phase difference. So this is a formula to explain this phased array antennas. So this is mainly composed of the element factor and the array factor. And the element factor is directivity of the each antenna. And the array antenna is expressed with this equivalent equation. And so if we put the same each antenna in same distance, and we can calculate the merge of the each radio waves from the antenna by this equation. So usually, of course, for the very complex and very high beam control, sometimes we control the amplitude. Like I mentioned in the morning session, when we would like to control the beam efficiency with the amplitude taper, we would like to control the amplitude. But for just to control the beam direction only, we usually control the phase in each antenna. And as a result, after transmitting from the antenna, radiated wave are merged into the one beams. So this is one calculated example of this equation. So this is a beam pattern of the phased array antenna. Now we control the beam just in front. And this is a beam pattern of each antenna element. And here it's easy to understand. Beam pattern is a little bit wider than the beam pattern of the array antenna because we merge a lot of antennas, a lot of radio waves from the antenna by the rule of this array factors. So as a result, we multiply this element factor and array factor, and as a result, we get this beam pattern. And when we control each phase or amplitude, we can change this array factor. And as a result, we control the beam direction and we control the form of the microwave beams. So this is an experimental result and theoretical result of the beam pattern of the phase array. And where we focus on radiated beam just in front. Here you can see theory and measurement results are very matched. And when we control in this case, direction is minus 20 degrees. We can control the direction, and 40 degrees, 60 degrees, we can control the beam direction. So this is caused by the change here, caused by the change of the phase and the amplitude only. And all antenna, they are not moved. And just by change of the phase and the amplitude, after the merging all radio wave with change of the phase and amplitude, we can control the beam direction and we can create a new beam pattern, like a flat top beam or the other. So this is a very basic theory of the phased array antenna. And from here, I would like to introduce a very important device, circuit, phase shifters. So phase shifters can control each phase of the input radio wave from the source to the antenna. We usually install this phase shifter between antennas and the source or the amplifier. And we install each phase shifter in each antenna. And this is a historical review of the phase shifters. Before 70s, there was no phase shifter because we cannot develop the phased array antenna. And around the 70s, ferrite, maybe you know, it's a very famous material to change the permittivity mu by change of the magnetic field added. And to add the ferrite, as a result, we can control the phase inside the waveguide mainly at that time. And after 70, some microstrip antenna and a microwave circuit was born. And in here, we developed the digital phase shifter with a pin diode or capacitance, etc. And now we use a very similar phase shifters with a diode or capacitance. I'll show you the later. And after 80s, we merged this diode, capacitor, circuit, etc., into one IC, monosilic microwave integrated circuit. So now you can buy the very small one chip of the phased array antenna on the website. And after the success of the MMIC phase shifter, now we have two big trends. Because this pin diode, FET, or capacitance includes some losses on the circuit. So to reduce the loss in the circuit or on the device, some people propose instead of the diode FET, MEMS, microelectronics mechanical system will be used for the phase shifter. So maybe some of you know, inside the device, we can change the shape of the line and like a switch, and we can use this MEMS, electromagnetic mechanical system as one part of the phase shifter. And the other line is digitalized. This is a digital. This digital means we can divide the 0 to 360 degrees phase into some digital value. But here we use a real digitalized radio wave we will control with some MMIC technology. I will show you later. So this is a brief history of the phase shifter. And recently, mainly this digital phase shifter or in the MMIC are used mainly recently. So this is a very simple line switch type digital phase shifter. As you know, radio wave will propagate even in the circuit. And radio wave propagate by change of the time and position of the position. And it means when we control the phase of each radio wave, easiest way to change the phase is to change the propagation line, length of the propagation line. So we install the switch. Sometimes we use a pin diode or the other, and in each line there are some difference of the length. So when we control the line, length of the line, and we can change the phase of propagating line. And we combine this line like the 22.5 degree line and a 55 degree line, 90 degree line, etc. And totally we can control the all phase 0 to 360 degree phase totally in this phased array. And we have the other phased array because in this case, in this switch, there are some losses, real losses, especially in pin diode. So if we use this phase shifters, loss factor is only 2 points. But if we develop this phase shifter to control the phase from 0 to 360 degrees, there are some losses 1, 2, 3, 4, 5, 6, 7, 8 loss factors. So this is a very lossy circuit, unfortunately. So now the other type of the phase shifter was proposed to change the impedance by change of the line open and close with change of the pin diode. And when pin diode on, this stub becomes an open stub. And if pin diode is on, it becomes a short stub. And when pin diode is open, this stub becomes open stub. So short stub and open stub impedance are very difficult. So by change of the pin diode, totally impedance of this circuit changes, and as a result, phase changes. This is named the rotated line type digital phase shifter. And sometimes there are a lot of interesting phase shifters. For example, this is a developed MMIC phase shifter with a rotated line type. Here you can see the pin diode and some stubs there. And this is the other type of the changing line phase shifter with help of the ratless circuit, etc. And in this paper, they can control the phase from 0 to 315 degree, and etc. So this is a typical phase shifter. And when we develop the phase array antenna, this phase shifter is very, very important. But as I mentioned before, it involves a lot of loss factors in pin diode or the other. And additionally, this is a very complex circuit, and this is a little bit expensive circuit. So recently, so this is named a digital phase shifter, but we control the line length of the impedance as an analog value. So in this meaning, this is not a digital phase shifter. This is still analog phase shifter. So recently, some of you know the word of the MIMO or massive MIMO, multi in, multi out, like phased array antenna system for wireless communication. For example, 5G or 6G mobile communication or Wi-Fi. Maybe you can see Wi-Fi based station in your room, and now you see the 3 antennas in your room's Wi-Fi based station. And from 3 antennas, they control the phase and they control the path length in this MIMO system. So this is mainly to control the path length in the multi-path circumstance. And for the wireless communication, they don't mind efficiency. So they only control the beam direction and path length to carry the information on the carrier. So in this case, this is one example of digital beam former. And so when we buy this chip, it is to control the beam form. But in this chips, this is a simple diagram of this digital phase shifter named the IQ modulator. And when we input the signal, and once we divide this signal into 2 lines, and we add the gain tuner, and we divide the sine sigma, sine theta, and cosine sigma from the radio waves. As you know, so radio wave can be explained with E minus J kz minus omega t. So it means radio wave can be explained with sine cosine theta plus J J sine theta. It's so, and with help of this real factor and imaginary factor I and Q, we divide the radio wave once, and we control the gain, and again we match this gain controlled to signal, and as a result, we can control the phase from the merged signal. So this is a very simple explanation of the digital beam forming networks. But for wireless communication, it's very simple and very low cost and very good phase shifter, like phase shifter. But this is a problem, gain tuner. So usually it's not a passive, it's not an active gain tuner, and it's a passive gain tuner. Just decrease the power only. So originally, for example, we input, for example, amplitude is 1 radio wave, and we divide this signal into 2, and we control the gain. For example, this line keeps at 0.5, but this line keeps at this line decrease the amplitude to the 0.3 or 0.2, for example. As a result, we can control the phase. So efficiency is very, very poor, unfortunately. So sometimes in the WPT startup company, they adopt this digital beamformer because cost is very, very cheap. But from the viewpoint of the efficiency, I don't like it. So if possible, we would like to use this analog type digital phase shifter to keep a high efficiency. So this is a very important element for the phased array antennas. And from here, I'd like to introduce a usual phased array antenna with semiconductors. So this is examples of the phased array antenna developed in Japan, mainly for wireless power transfer. Because now there are a lot of phased array antenna. For example, in your room, Wi-Fi adopt digital beamforming network and massive MIMO as a phased array antenna. And as a military system, they adopt a digital beamforming network with a very very high loss, or they don't mind just efficiency of the circuit in the phased array antenna because they just keep the information quality only. So, but for the wireless power transfer, as I mentioned, efficiency at the circuit behind the phased array antenna are most important. So in this viewpoint, we Japanese Kyoto University and colleagues developed some kind of the phased array antenna. And usually we adopt a semiconductor to control the phase or to amplify the microwave signal as a power. And as I mentioned yesterday, history of the phased array antenna for the wireless power transfer was studied from the 1992 for the airplay experiment named Myrax, when I was a master course student. And at that time, amplifier in the phased array antenna was with gallium arsenide. And about 10 years later, we developed a split solar power satellite modulator with help of JAXA, the other Japanese colleagues. And at that time, 1992, frequency was 2.4 gigahertz. And 10 years later, we increased the frequency. In this morning, I explained when we would like to, if we would like to increase beam efficiency, higher frequency is better. If we have a good high efficiency circuit. So during this 10 years, we get very good circuit technology with higher frequency. So at that time, we adopted a 5.8 gigahertz. And at that time, we didn't have enough budget. So we bought the semiconductor, gallium arsenide or the other. But about 10 years ago, we got much budget from Japanese government, and we developed gallium nitride itself as a wideband gap semiconductor. So we can increase the efficiency, and we can increase the accuracy of the phase control, etc. And we keep this development now. And in parallel, to reduce the cost, we, Kyoto University, mainly proposed the phase array with the magnetron, and this is the second topic in this lecture. I will explain later. So usually, this is a typical diagram of the phased array antenna. We have two kinds of the phased array antenna. Usually, we have one small microwave or radio wave power source. Typically, 1 milliwatt or less power is generated in one chip. And we add a power divider, and after the small power generator, we add the phase shifter. And after the phase shifter, we add the microwave amplifier. to increase the total power and isolate it, etc., and antenna at the last stage of the phased array antenna. It's a typical phased array antenna. But we have the other kind of the phased array antenna. Originally, we can generate high power microwave. For example, we sometimes adopted a magnetron, etc. 100 watt directly or 1 kilowatt directly. And in this case, we don't need any power amplifier, but we have to install the phase shifter at the high power stage. Because even if we divide the generated power from, for example, 1 kilowatt to 1,000 antenna elements, each power is still 1 watt in this case. So in this case, in phase shifter, they control only 1 milliwatt in this example. But in this case, this phase shifter can treat the over 1 watt power, and the loss is very high in this case. So, but this system is very cheap system, because when we install a lot of microwave amplifier, of course, we need some budget to develop the amplifier. But in this case, power source is high power source is only one. It's very simple. So we can choose both in consideration of the loss or accuracy or the other phase array problem. But usually, with help of the semiconductor, we choose this kind of the phase array antenna. And I would like to introduce a Japanese case. For example, this is a Myrax experiment as I introduced yesterday. And this is a beam pattern from this phase array antenna. Here you can see there are a lot of smaller antennas. Antenna and phase controlling circuit is the same. And from each antenna, we control the phase in this case. And the frequency, I have. And the frequency was at 2.411 gigahertz. And we installed 228 antennas. And in each 3 antennas, we installed the 1 phase shifter and amplifier, etc. So as a result, this is the measurement data of the beam form, and we can control the beam direction. And so at last, we could fly this fuel-free airplane named Myrax about 30 years ago. So this is the world first phased array developed mainly for the wireless power transfer in the world. And so this is a circuit efficiency at the microwave amplifier at that time. And so as I mentioned, at that time, we adopted the gallium arsenide. And some students developed this amplifier. And at that time, efficiency was only 40% from the source to the amplified amplifier. So 40% is not good, but we keep developing a good amplifier or phase shifter year by year, and now we can increase the efficiency of the amplifier, etc. But this was 30 years ago result. And we use the same phased antenna, phase amplifier and phase shifter antenna system into the next year's rocket experiment METS. Because for this experiment, we have this good phase array antenna, and we can use the same phase shifter and amplifier system for this rocket experiment to reduce the cost. So yesterday I showed you the same, and each antenna transmits a controlled microwave, and we control the beam direction in space. And this is a measurement beam form and calculated beam form from this strange shape of the antenna. This is a calculation result in my bachelor thesis, so about 30 years ago. So, and power density decreases by distance at distance, But as I mentioned again and again, this is not a real attenuation, decrease of the power. This is caused by the expansion of the power beam. So from this antenna, beam shape becomes very strange, but we can control the beam direction, and this ISMS rocket experiment was succeeded. And next, with help of JAXA budget, we developed a split solar power satellite modulator demonstrator. And in this case, I said again to reduce the cost. So in this case, we adopted the other phase array diagram. We add very high power amplifier, only one. And after high power amplifier, we install the power divider or feeding network into 100 phase shifter and antenna. And we install this phase shifter after the power divider only. And at last, from this antenna, we control the beam direction. And the parameters are there. And so compared to the previous two experiments, we increase the frequency 2.4 to the 5.8 gigahertz. And this is a beam pattern measured and theoretical result of the split. Here you can see it was the same. And we can control, we could control the beam direction in this split experiment. Here you can see there are some error difference between the theoretical result and the measurement result. It is caused by the mutual coupling effect of the other real error factor in the phase array antenna. So in this split, efficiency was too bad because we installed a very high power amplifier, and after the high power amplifier, we installed a lossy phase shifter. But this is a very good demonstrator of the solar power satellite. And about 15 years ago, we, Kyoto University, got a very huge budget to develop gallium nitride semiconductor itself. So by help of the Mitsubishi Electric, they can develop a good gallium nitride semiconductor, and we could develop this phased array antenna with newly developed gallium nitride MIC. And the frequency was a 2.50, no frequency. Our frequency was a 5.8 gigahertz at the time, and we installed 256 antennas here. And each gallium nitride amplifier can produce the overall 7 watt and with 70 conversion efficiency. And this is a measurement characteristic of the power altitude efficiency, amplitude efficiency at the gallium nitride. And here we reach the 70%. So this is a very good phased array developed in Kyoto University and Mitsubishi Electric. And this is a beam forming pattern. This is a simulated and measured result. And so here you can see we control the beam direction. And this is a H cut and V cut. So it means we can control the beam direction, x-axis and y-axis, 3-dimensionally. And based on this Kyoto University's phase array, in the METI project phase 1, as I mentioned yesterday, we Japanese developed a very thin and higher efficiency phased array antenna. And this is a very complex circuit inside this phased array, but within 2 centimeters only, we installed all amplifier beam forming network, phase shifter, antenna, etc., into this thin thickness. So this is one reaching point of the phased array for WPT in Japan. And from here, I would like to introduce the other way to develop the phased array with low cost, with help of the microwave tubes. So, of course, some of you now do not know what a microwave tube is. Microwave tube is this vacuum tube to generate the microwave itself. And we have some kind of the microwave tube magnetron is usually applied in your house, microwave oven. And the other type of the microwave tube is a Crystron or TWP, tropic wave tube, or gyrotron, etc. And for wireless communication, now they do not apply the magnetron. About 50 years ago, they applied the Crystron as a source of the wireless communication. But recently, they all use a semiconductor. But still, for the microwave oven, we use the magnetron. And for the wireless communication from the satellite, broadcasting from the satellite, this satellite has a microwave tube, tropic wave tube TWT, and they transmit the wireless communication radio wave from the space to the ground. So, and we, Kyoto University, focus on the magnetron. Detail of the magnetron will be explained tomorrow. But today, I would like to introduce briefly the phase array technology with a magnetron. Because magnetron is a very, very cheap device compared to the semiconductor. And magnetron achieves a very high efficiency with very, very low cost. And this one magnetron can generate over 500 watt or 1 kilowatt. So these parameters of the magnetron are very excellent compared to the microwave devices, cost, efficiency, power. But only one problem is we cannot control the phase, or we cannot control the amplitude itself of the magnetron. Because and additionally, waveform from the magnetron was not clear. This microwave from the magnetron has a wide frequency spectrum and a little bit noisy. So, now the magnetron applied only in the microwave heating in your home. So, but these merits are very excellent, we think. So we consider how to reduce the noise and how to control the beam phase and frequency. So originally, William Brown, please go back to the 60s. William Brown proposed the phase control magnetron. He named it a magnetron amplifier in 60s. And we ran a lot from the William Brown technology. And as a result, and we add the new technology to this magnetron amplifier named by William Brown. We succeeded in developing the phase and additionally amplitude control magnetron with help of a PLL feedback loop and injection locking. I'll explain the detail tomorrow. But this is a simple diagram of the magnetron. We use the same magnetron for the microwave cooker. And we add the controlling circuit of the injection locking and the PLL feedback. And as a result, we can control the phase and the amplitude of the magnetron. And someone consider, for example, this is one example of the developed phase control magnetron. And compared to the microwave semiconductor, it seems very big. So with help of a Japanese company, we developed a very small type of the phase control magnetron. Inside this box, please compare the size with this CD. This is very small, and from this small size, we can create a 270 watt at 5.8 gigahertz. And inside this box, we install the all control circuit, magnetron, high power source, etc. So with help of this technology, at first, we demonstrated the phased array with the two magnetrons. And theoretically, we can control the beam direction with at least two elements. So here you can see we control the beam direction at 90-degree focusing point and 80-degree focusing point. And this is a demonstration movie of the developed two element phased array antenna with two magnetrons. We put the two receiver here, and these are rectifier, and this motor could be driven by the microwave power. And now we control the beam direction only this line, and next we change the beam direction to this line only. So now here is the microwave power from the magnetron, and here So we change the direction by change of the phase of the magnetron. So this is the phase control data inside the computer. So we show we can develop the phased array antenna with a magnetron, which is considered as an old technology, but it's very high efficiency, high power, low cost. Low cost is most important. We can develop the phased array antenna with magnetron. And with help of the Japanese government budget, we developed not a 2-element phased array with magnetron, but a 12 magnetron phased array. And we can control the direction. And at that time, in this system, we adopted the normal Kuka type magnetron. Frequency was 2.4 gigahertz. But next year, we increase the frequency to the 5.8 gigahertz. It's the same magnetron, but frequency is only the change. So now we have in Kyoto University, we have a 5.8 gigahertz magnetron phased array in my laboratory. So this is a very interesting technology I think. And with help of the magnetron, we demonstrated one interesting experiment outside of the laboratory. So we installed a 2-phase controlled magnetron phase array antenna on the airship. And our image of this experiment is to help to support the emergency area or disaster area. When heavy earthquake hit the Japanese Kyoto or the other area, unfortunately, lifeline, including a power line, gas line, water line, were cut. So in this case, they need the power source, electricity itself. Even if you have a mobile phone or Wi-Fi Wi-Fi base station, if there are no electricity, we cannot communicate each other outside of the emergency place. So in this case, we bring power source from the sky. And from the sky, from the airship, we transmit the wireless power to charge the mobile devices, to communicate each other. And we succeeded in the charging, wireless charging on the ground of the smartphone here. And it was about 15 years ago experiment. And this is a measurement data of the beam pattern. This is a theoretical beam pattern, and this is measured beam pattern. In this case, we adopted a 2 big antenna array. And here you can see we can control the beam direction only with the magnetron technology. And in parallel, Japanese government keeps the development of the magnetron phased array. And yesterday I mentioned, and Mitsubishi Heavy Industry Group carried out the demonstration, the 500 meters WPT beaming demonstration with magnetron technology. So these are based on the Kyoto University and the William Brown technology. And I found the other interesting phased array with other microwave tube, TWT. So as I mentioned, usually TWT, traveling wave tube, is installed in the satellite for broadcasting. But a Japanese group, developed a mini TWT to develop the phased array. Usually on the satellite, they input only one TWT to transmit the broadcasting TV wave. But they developed a phased array with a mini TWT. But I found only one this paper, and so I want to find the other phased array with a microwave tube. But now I only find this paper from Japan. So this is a real developed result, mainly in Japan. And from here, within 5 minutes, 10 minutes, I would like to introduce technology, how to keep the high beam efficiency with phased array. Because as I mentioned, theoretically, it's easy to control the beam direction or beam form by the phased array antenna. but in the real, there are some error factors. And we can divide the error factor into two. One is a theoretical error factor. Without any phase error or trouble with the element, theoretically, some problem occurs. For example, grating lobe, it's the same power as the main lobe, outside of the main lobe, etc. And in the real developed phase array, of course, in circuit or in antenna, there are some phase error or trouble with the element. Pointing error and including a side lobe occurs in the real. So within 5 minutes I would like to introduce this error factor or unexpected error to decrease the beam efficiency. First of all, big problem is a grating lobe because, as I mentioned again, this is a theoretical beam forming formula to estimate the beam form with one antenna element factor and the array factor. And here you can see when we put the antenna in the space with a dn, and if we put the equal element spacing, it's easy to calculate the element factor from this equation. But this equation occurs some problem. So in this case, as I mentioned, in this case, we can put the small antennas within a small antenna spacing. But in this case, each antenna propagates large power. And in this case, we should put larger antenna size because in each antenna produce much power. So in this case, we usually put the antenna with a large or long element spacing. And based on this equation, if dn element spacing is larger than half wavelength or one wavelength, theoretically, this grating lobes occurs. Grating lobes is the same power as the main lobe, and this is caused by the equality of the cosine theta. So as you know, 0 degree and 360 degree is the same phase and the same value. So if d becomes very large, when we change the initial change of the phase, in this case, EQ is the same case by periodically of the cosine theta when dn is equal spacing. So based on this equation, it's easy to estimate how much grating lobe occurs in how degree we control the beam direction. And based on this equation, if element spacing d is shorter than quarter wavelengths, grating lobes never occur. This is the best phased array antenna. But usually, we cannot put each antenna within a half wavelength element spacing because originally antenna is a resonator. Typically, we have a half wavelength as a dipole antenna, etc. So you usually put the element spacing with between half wavelengths or one wavelength. And when we put the antenna with a space of the over one wavelength, grating lobes always occur. So when a grating lobe occurs, beam efficiency suddenly decreases because our target is only one. And if there is no grating lobe, almost all power is transmitted to the one user. But suddenly, grating lobe, same power as the main lobe occurs. For example, one grating lobe occurs, beam efficiency becomes half suddenly. So how to suppress the grating lobe? Of course, short element spacing is better. There is no problem. But if we cannot put the antenna element within one wavelength, we have to consider how to suppress a grating lobe. There are a lot of good research results in the world and in Kyoto University, but today I don't have enough time. So I would like to introduce one recent research result in Kyoto University. So we put the antenna, in this case, we put each antenna with space of the 1.4 wavelength. It is larger than one wavelength. And in this case, when we control the beam direction, grating lobes occurs. But we put a parasitic element. Parasitic element means just a metal only. There is no power source, there is no phase shifter, there is no circuit behind this metal. But when we put the metal between long spacing antennas, mutual coupling electromagnetically occurs between the powered element and non-powered parasitic element. And as a result of the mutual coupling, this metal suddenly becomes antenna, because here we have a current distribution. So in this case, between the long distance wavelength element spacing, we can put the similar antenna, parasitic antenna, and as a result, we can reduce the element spacing. But we don't have much phase control circuit in this case. So we can reduce the cost of this phased array antenna. And we simulated this antenna with a parasitic element. And as a result here, this is a normal phased array with all fielded antenna elements. And in this case, we can focus the antenna into one point, and it's very good phased array antenna, no problem. But when we use the parasitic element, we feed microwave power only in this antenna. And between antennas, we add the metal only, and by the mutual coupling, we create the new antenna here. And as a result, we can create a very similar beamform with a half microwave circuit. So this is our interesting proposal. New low-cost phased array antenna with a parasitic element. And this is an experimental result, and the simulated result are very matched. So I think this is a very interesting technology. But to revise or to update this technology, because mutual coupling was a little bit smaller than we expected. So my student proposed a very tight mutual coupling line between metal and fielded antenna. And as a result, we can control the beam direction by change of the fielded antenna only. So this is our Kyoto University proposal to suppress a grating lobe with keeping the low-cost phase shifter with a long phase spacing. So that's all my today's talk. So today, now I introduce a phased array antenna technology. And when we have a good phased antenna technology, this is the best technology for advanced WPT business or for wireless, for solar power satellite, because we can increase the beam efficiency even if user move or transmitter move to somewhere. And we can suppress the unexpected radiative wave, and we can keep the safety for the radiative WPT system. So for the advanced WPT business or the solar power satellite, this phased array antenna, and hopefully with a low cost is expected. So that's all my talk. So thank you so much. So do you have any question or comment? Yes, please.
Sir, this proposal will increase the cost than if you are using parasitic.
Oh, no. In this case, cost is the same as this. No. cost is the same as a phased array antenna with grating lobe, low beam efficiency, because we only at the metal only. So usually we use the phase shifter, amplifier, etc. in each antenna, as I mentioned. And so the cost is decided by the number of the circuit and the antenna and the cost of the circuit itself. So we have to multiply the number of developed circuit and the cost of the circuit. But in this case, we use a half number of the circuit, and the cost is a half compared to the normal phased array. And we add only the very low cost or without any cost metal only. So compared to this normal phased array, number of circuit becomes half. It means cost will be half. So we propose it.
And slide number 45.
So number 45. 45. Are
Yeah, the next one, I think. 46. Yeah, this one. We should also match the impedance of each and every circuit
Yeah.
here. And whenever the errors will come, then we should shift the phase.
Yeah.
We should again match the impedance of every circuit.
Yeah. So if we control the beam direction, I agree with you. So impedance in each antenna changes by the mutual coupling or etc. So we have the other technology to suppress the mutual coupling, etc. Today, I didn't bring this technology, but in Kyoto University, one of my PhD students has already developed the antenna to suppress the mutual coupling, for example. But now there is no best technology to suppress the mutual coupling to change the beam direction. So it's a very good research topic for future.
And it
Not
will
only
become costly again.
So yeah, we have some way. So usually we consider the cost, but so 2 lines of paper, you don't mind any cost. So,
Yeah.
but I would like to expand the WPT business, solar power satellite, etc. Outside of the university. So we, Kyoto University, is always considering the cost of the circuit or phase array antenna, etc.
Okay, thank you.
Any other query? No? Okay. Now, thank you very much for this talk. We will have a tea break of 10 minutes, then we'll meet again.
So after 10 minutes break,